In today's program, we'll answer the three following questions. How does our organism defend itself against the cold? How do low temperatures endanger some of our technologies? And finally, yes or no, is freezing the sacred gateway to immortality? Several animal species have developed ways to adapt to extreme cold. Hibernation is one. Man, however, cannot hibernate. But even if he is without fur or down, he does have remarkable ways of adapting to cold. At birth, an infant experiences a painful reality. He discovers cold. During gestation, the only temperature the fetus had known was the constant 37 degrees Celsius warmth of his mother's womb. Then he is suddenly thrust into a much colder world than his former environment. For us all, that first contact with cold is just the beginning of a lifelong battle. All our lives, we have to maintain our internal organs at the same temperature as our mother's womb, despite the constant variations in temperature around us. Our body produces its heat through a series of countless chemical reactions. For example, in 1 hour, our liver produces as much heat as an electric heater does in 2 minutes. That heat, called metabolic heat, is distributed throughout the body by blood circulation. It is then dispersed outside through our skin. When the ambient temperature is near 20 degrees Celsius, our metabolic heat compensates for our body's heat loss. The body therefore easily maintains its 37 degrees Celsius temperature, which is necessary for our vital organs to function properly. When the ambient temperature decreases, our production of metabolic heat is no longer able to make up for the heat lost through our skin. A series of physiological reactions to combat the cold is then set in motion. These reactions are triggered and controlled by a particular part of the brain called the hypothalamus. The hypothalamus acts like a thermostat. Its cells are bathed in a flow of blood that comes directly from the torso. It therefore detects any variation in temperature in the vital organs. The hypothalamus is also connected to small receiving organs in the skin called Krauss's corpuscles. When in contact with the air or cold objects, these organs emit nerve signals. Picked up by the hypothalamus, the signals inform it of the drop in external temperature. Alerted, the hypothalamus sets off a first reaction, vasoconstriction. Vasoconstriction is a decrease in the diameter of the blood vessels in the skin, face, and extremities. By reducing the surface of the vessels that are exposed to the cold, this reaction cuts down on heat loss. Also, vasoconstriction allows the body to maintain warm blood in the torso. The hypothalamus also causes contraction of the tiny muscles located at the base of the hairs that cover our body, making the hairs stand on end and giving us what we call goosebumps. Goosebumps thicken the layer of tepid air that normally covers the surface of the body. That layer of air helps to insulate the body from the cold. However, if the outside environment is both cold and windy, that layer of protective air disperses. It is then no longer enough for the body to conserve its heat. It must produce more of it. To do this, the body uses muscular contractions. In our muscles, in the presence of oxygen, glucose is burned, releasing carbon dioxide and steam. This chemical reaction releases energy, exactly like the combustion of wood. While part of that energy serves to supply the muscular exertion, most of it is released in the form of heat. We can fight off the cold by conscious and voluntary muscular contractions, but also by involuntary contractions, shivers. Shivers help to increase the amount of heat produced by the body. Shivers are as intense as the wind is strong. All these mechanisms generally enable us to withstand intense cold until we can find shelter. However, researchers are noticing that man's resistance to cold is far more complex than it looks. Experiments have shown that repeated exposure brings about a gradual adaptation to cold. That adaptation can be achieved by submerging a subject into cold water, for example, every half hour. After a certain number of immersions, the subject is placed in a cold room. The subject's various physiological aspects are then measured, such as his internal and skin temperatures, loss of heat, as well as his oxygen consumption. Such experiments have demonstrated that man can substantially increase his adaptability to cold when exposed to cold surroundings on a regular basis. People who are conditioned to the cold only begin to shiver after longer exposures or when the temperature drops way down. No matter how efficient his own physiological mechanisms are, man would never have been able to settle in all his habitats were it not for those sophisticated technologies, clothing, and shelter. Physiologists consider man to be a tropical animal, which would explain his preference for the warmer climes of his origins. Our body has a considerable capacity to adapt, but it isn't foolproof. In some circumstances, the body may become unable to sustain its production of heat. When our body temperature reaches 32 degrees Celsius, our defense mechanisms cease to function. 25 degrees Celsius means sure death. Cold is no mean adversary for the human body, and the same applies to a number of our technologies as well. For centuries, our species has been able to adapt to the most rigorous climates in the world. Essentially, our survival in these inhospitable surroundings is based upon various technologies that enable us to work, move about, and be comfortable, even in the polar regions. Even though the technology is constantly being refined, the cold still remains a barrier to human activity. That barrier is often related to a well-known natural phenomenon, the transformation of water into ice. For example, we know that the ice that forms on the surface of our northern waterways and polar seas is a serious inconvenience to navigation. That inconvenience is due to an amazing property of ice. It floats. This physical phenomenon is explained by the particular chemical composition of water. Water molecules are made up of one atom of oxygen connected to two atoms of hydrogen. When the temperature is above 0 degrees Celsius, the water molecules slide one against the other relatively freely. The water is then in liquid state. However, when the temperature falls, bonds begin to appear between the water molecules. Indeed, the atoms of oxygen of water molecules have a negative electrical charge, whereas the atoms of hydrogen have a positive charge. Owing to the attraction between opposing charges, the oxygen atoms of every water molecule tend to bond with the hydrogen atoms of the surrounding molecules. These bonds increase in numbers as the temperature decreases. Suddenly, at 0 degrees Celsius, the water molecules get together to form an orderly network, ice. As they do this, however, the water molecules move away from each other. Due to the structure of ice, the water molecules are further apart in ice than in liquid water. That's why ice is not as dense as water and why it floats. To study the possible impact of ice on ship hulls, the researchers use experimental tanks in which they cause a layer of ice to form on the surface of water. That layer of ice has, on a small scale, the same characteristics of hardness, density, and texture as a real ice floe. By letting a projectile with observation instruments fall onto the ice, they can assess the forces ice exerts on a ship's hull. They can therefore determine how much resistance the hull of an icebreaker should have. Ice can be even more threatening to human technologies. For instance, ice will form on the wings of planes. The aircraft are then considerably weighed down, so much so they can actually crash. Ice may build up before the plane's takeoff, for example, after a downfall of freezing rain. If this occurs, it can be melted by hosing the wings down with antifreeze. However, ice can also build up on the wings during flight. Contrary to popular belief, very pure water can remain liquid at temperatures way below 0 degrees Celsius. That water, said to be in supercooling, only freezes if a cold object or an ice crystal is placed in it. The object sets the crystallization process in motion, offering the water molecules a support on which they can begin to bond together. If this phenomenon goes unchecked, it can cause air catastrophes. For instance, while cloud temperatures are seldom above 0 degrees Celsius, clouds are composed of tiny drops of liquid water that does not freeze in spite of its low temperature. However, when an airplane goes through a cloud, its wings and fuselage provide a basis upon which the droplets of water can attach themselves to form ice. The scientists are studying this occurrence in a facility called an icing tunnel. This device can project a cloud of mist-like droplets of water at a speed of up to 500 kilometers an hour, and at a temperature as low as -35 degrees Celsius. By placing a piece of wing or any other such airplane structure in the device, they can simulate the buildup of ice on the objects in real flight conditions. With this apparatus, the scientists hope to better understand the conditions which lead to ice formation and to find out how to prevent the dangerous effects of ice. For instance, they are developing sensing devices that can detect ice buildup and identify the kinds of precipitation falling on a plane's wings. Alerted by the sensors, a pilot could then take the appropriate steps, such as calling the de-icing team if the plane is on the ground, and if it is airborne, activating the onboard de-icing system. Cold has its advantages. Just think of the role it plays in preserving our foods. In frozen food, chemical reactions are slowed down and bacterial activity thwarted. The product ceases to deteriorate. It can remain intact for months, even years. Little wonder then that this process has been considered for a variety of other uses. There are people who claim that by freezing the human body, we could achieve mankind's oldest dream, immortality. Those who would attempt such an experiment would, alas, be bitterly disappointed. In all probability, their carefully preserved bodies would be more dead after freezing than they were on the day they died. We owe that assertion to specialists in the biology of low temperatures, or cryobiology. These researchers have indeed proven that freezing causes irreparable damage to living cells. The damage occurs when the water both inside and outside the cells freezes. Sharp-edged ice crystals first form inside the cells. The crystals tear to shreds the membranes and inner compartments that play a vital role in the functioning of cells, so that once they have thawed, the cells can no longer function. Crystals can also form in the liquid that surrounds the cells. In themselves, the crystals do not threaten the cell structure, but they cause them to dehydrate. Indeed, ice crystals are made up solely of pure water, whereas the liquid around the cells contains several dissolved substances. So as the crystals grow in size, the dissolved substances become concentrated. Following the increase in concentration, the liquid water in the cells tends to move outwards. The osmosis causes the cells to become dehydrated. Below a certain critical threshold, that dehydration can seriously damage the cells. Moreover, when they thaw, the cells are so quick to reabsorb the lost water, they can actually burst. Because of all these phenomena, freezing a human body would cause irreparable damage. Now, cryobiologists are pursuing a less ambitious objective, the freezing of human organs for transplants. Their hopes lie in the amazing faculty of certain animals to withstand congelation. For example, the Rana sylvatica frog, or tree frog, a small amphibian that inhabits the northern regions, spends a part of the winter frozen as hard as ice. Its heartbeat, respiration, and movements are completely halted. As soon as the temperature rises above the freezing point, all the animal's vital functions resume normally. What enables the tree frog to survive freezing is the secretion of a number of protective substances. Those substances contain two types of proteins. First, nucleation proteins are secreted outside the frog cells. These proteins trigger the formation of tiny ice crystals outside the cells. Furthermore, the researchers believe that, as in the case of certain insects, the animal secretes other antifreeze proteins which would in fact literally coat the little ice crystals that have formed. These would have the effect of slowing down the crystal's growth. The combined action of the nucleation and antifreeze proteins would thus contain the formation of ice outside the cells. To protect the inside of its cells, the frog uses another substance. When the frog begins to congeal, glucose rapidly builds up inside and outside the cells. Glucose has the effect of lowering the cell's freezing point. The cell's water thus remains in a liquid state, which prevents the formation of dangerous ice crystals. When they thaw, the cells are therefore able to function normally. By studying such mechanisms, the cryobiologists have learned how to preserve certain human cells and tissues. For example, since 1949, scientists have been able to preserve animal and human sperm by freezing it in liquid nitrogen at -196 degrees Celsius. The technique they use consists of mixing the sperm with a glycerol solution. Like glucose, glycerol is a cryoprotector, which means it protects the inside of sperm cells from the effects of congelation. The temperature of the samples is then gradually lowered to -100 degrees Celsius, after which they are plunged into liquid nitrogen, where they can remain intact for years without any noticeable loss of vitality. Unfortunately, preserving whole human organs by freezing may prove far more complex. Human organs contain thousands of kinds of cells which react differently to freezing. The researchers are trying to develop ways to protect every type of cell, but the formidable obstacles still facing them give us reason to believe that the freezing of the whole human body will, for many years to come, remain within the realm of science fiction. You may have observed during a heavy snowfall the shape of the falling crystals. There are needles, stars, pyramids, little shells. Snow crystals form in clouds. They build up around a solid particle, often a speck of dust. When they become too heavy, they fall. The crystal that melts on your hand underwent all sorts of variations in shape during its descent. Some scientists have fun putting them into dozens of different categories. And me, I just have fun looking at them.